Hello everyone. Thank you for joining today's webinar titled Innovation in Isolated Field Bus Communications for Harsh Environments. My name is Anup. I am a field application engineer in Analog Devices, India team. I hope you will find this presentation interesting and informative as you consider existing communication port design and move forward with the new designs in the future. This is going to be our agenda for today's presentation. We will start with a brief summary of our key customer concerns and trends in field-based communication. Then we will examine the importance of electromagnetic compatibility in various applications. We will then discuss about various challenges like high voltage transients, electrical noise, radiated emission, and installation errors. We will look at the new generation RS485 transceivers designed to meet all these challenges. After the presentation, we hope our guest will have an understanding of EMC standards for industrial communication ports and how our products deliver industry-leading robustness. You can have your questions typed into the chat window anytime during the presentation. We will discuss those questions towards the end of presentation. Okay, let's start. So this slide presents a summary of the key customer concerns and trends that we are seeing in field bus communications. The primary concerns are robustness to electromagnetic transients, installation errors, as well as noise immunity. As you know, meeting EMC standard is the number one challenge for industrial communication ports. The key customer trends that we see in this field are increasing demand for interface solutions on smaller PCB area. Also, every project have less time available for iterative technology investigations. And as you know, the projects are expected to complete with minimum budgets as possible, with an aggressive and faster timeline to market. So in addition, higher data rate, increased robustness, and smaller packages are being targeted for some applications. Analog Devices team has been working hard on addressing these issues, and we will continue to do so in the future. Next few slides, we will be talking about electromagnetic compatibility, wherein we will briefly cover harsh environments, EMC, and some of its classifications, and a hierarchy of standards, and design for EMC. Okay. Basically, our transceivers are used in many applications: motor control, communication infrastructure, industrial automation, and building technology are some of those examples. As you know, there exist harsh electromagnetic environments in all these applications due to various reasons. For example, inductive and capacitive load switching, relay switching, lightning, etc. Here, the transceivers might get subjected to those conducted or radiated noise. So majority of these transceivers have global pins that go to the outside world. Means pins from ICs going out of the PCB, and they might be connected to an external cable which may be shielded or unshielded and might run for several meters to kilometers. So there exists a high chance that these cables might get subjected to high level of electromagnetic interference and transients. To ensure the proper working of the system, they must be EMC compliant. So there exist test standards to ensure reliable working of transceivers in such situations. Today, EMC is a great concern to product designers due to the stringent electromagnetic test standards, and it is not an easy task. Now, let us look at EMC and some part of its regulations. EMC is defined as the ability of an electronic system, firstly, to function properly in its intended electromagnetic environment. Secondly, it should not be a source of pollution to its electromagnetic environments. Okay. So, from that, we can understand that EMC has two aspects. One is immunity, and the second one is emissions. So, immunity is the quality of being immune to electromagnetic interference in its intended environment. For example, if the pulse with the distortion of a RS485 transceiver is not deviating beyond the specified limit during an electromagnetic interference, then the transceiver is said to be immune to that electromagnetic event. Immunity is tested against various cases. It could be against radiated or conducted noise, or it could be against transients like ESD, EFD, and surge. Testing a transceiver against plus or minus 60 volt is a plus or minus 60 volt overvoltage or misfiring is another example of fault tolerance test. Then emission. Emission can be in the form of radiation or conduction. This is the amount of electromagnetic energy emitted by the device. The purpose of controlling emission is to make sure that the energy emitted by the device is not adversely affecting any other devices within or external to the system. Government agencies and regulatory bodies like IEC, FCC, CISPR imposes these EMC regulations. So this slide basically shows the hierarchy of EMC standards. All the way at the bottom shows the basic standards. These are the generic standards or test conditions to achieve the electromagnetic compatibility. Each one describes a particular set of tests and all the requirements to carry out the test. So these are the standards or building blocks for higher level standards. Typically, they are the IEC 61000 4-4, 4-2, 4-5 tests or CISPR 16 publications. Generic standards are the next set of standards in the EMC hierarchy. These are the step up. These are one step from the basic standards and are defined for a particular environment, not for a product or family of product. For example, EN 61000-6-1 defines the immunity requirement for residential environments, whereas EN 61000-6-2 talks about the immunity requirement for an industrial environment. Next, we have the product family standards, and these are defined for similar products. For example, EN 55022 talks about emission standards for IT equipments. So in the hierarchy, next we have product standards. These are specific standards for a particular product. For example, EN 61800-3 defines requirement for an adjustable speed electrical power drive system, our VFDs. Then all the way at the top, we have manufacturer standards. These are basically in-house standards, and they prevail in automotive industry a lot. Each manufacturer has their own EMI requirements, and of course, all suppliers are bound to meet these standards. So, looking at the diagram in the left-hand side, it is evident that we should first focus on basic standards to comply all other standards in the hierarchy. And we will be discussing these generic standards in coming slides. Now, in this slide, let us discuss a bit on the concept of designing for EMC. In analog devices, we hear a lot of questions and concerns from our customers related to EMC. There were incidents where the whole product release is shifted for months together due to EMC issues. And as you know, doing design iterations for EMC cost you a lot. So we have to be very careful about it. Considering all these pain points, in ADI, we help resolve EMC issues for our customers by adopting design techniques that reduces EMC burden into our ICs. This actually helps the customers to reduce EMC certification time and enable them for a faster time to market. Let us take a look at how engineers approach EMC. Basically, there are two ways in which you can address EMC. Firstly, crisis approach. This is also known as band-aid approach, wherein EMC is considered only at the end of the design cycle. In this method, EMC issues are identified at a very later stage, and solutions implemented are very expensive. This approach usually shifts the product release schedule. Secondly, we have the system level approach. In this case, EMC is considered throughout the design cycle. Here, EMC is designed into and not onto the product, as against the band-aid approach. This is the most desirable and cost-effective method. However, technical design challenges associated with this approach is very tough, and designers needs to have a very good experience to accomplish this task. The graph on the top gives you an idea about the product development time, cost, and the technique to resolve EMC issues. As we move through the design phase, the available techniques are limited. Notice that at the beginning of the design, you have many available techniques to EMC, and it is inexpensive. So ADI wants to help our customers resolve EMC issues at the starting of the design cycle. In the subsequent slides, we will discuss IEC 61000 system level transients. They are ESD, EFD, and surge. Okay. Let us examine the IEC 61000-4-2, the electrostatic discharge immunity. By definition, ESD is the sudden transfer of electrostatic charge between bodies at different potential. It is caused by near contact or induced by an electric field. Here are two types of coupling mechanism by which ESD is induced into a circuit. First, air discharge with a rounded tip. Second, the contact discharge with a pointed tip. Due to better repeatability, contact discharge is the preferred test method. However, air discharge resembles a real-world condition. This can be easily understandable from above image, wherein a person's fingertip is almost similar to that of the air discharge tip shown right to it. But keep in mind that air discharge depends a lot on its environment, humidity, temperature, pressure, and rate of approach, etc. Hence, repeatability in air discharge is very difficult. This is the major reason to choose contact discharge over air discharge. Fine. The picture on the right hand side on top represents an IEC 61000-4-2 waveform for 8 kV contact discharge. If you look at the characteristics, you can find that it has a very short rise time, 0.7 nanosecond to 1 nanosecond. Note that within that rise time, the waveform is hitting 30 amps, and it has a pulse width of about 60 nanosecond. Table on the bottom side shows level and the associated air discharge and contact discharge test voltages in kilovolt. You will find that air discharge has different voltage rating against contact discharge. It is because The severity level for contact discharge is much severe than that of air discharge. Hence, a 4 kilovolt or 2 kilovolt air discharge is not equal to contact discharge of 4 kilovolt or 2 kilovolt. Moving on, this is the typical test setup for one of our isolated 485 transceiver. In this case, test is conducted with respect to ground one, and there is an isolation barrier present within the chip, and there is ground two, to which the internal protection mechanisms must provide a path to protect the transceiver from ESD transients. Chip is tested for two types of discharges. First is the direct discharge. This is the most severe test. Transient is injected directly to the device under test. In the second method, is the indirect discharge. In this method, transient is injected into horizontal and vertical planes, and this is a conductor type testing. That implies the ESD gun makes direct contact with the vertical and horizontal planes. And there are two 470 kilo ohm resistor connected to each end of the discharge path. This is to ensure complete disappear of the ESD energy after the event, ensuring more impact to the device under test. Typically, in ADI, we test the transceivers for a number of configurations. For example, we do the ESD test when the transceiver is powered on. We do it when the transceiver is unpowered, and we also do the test when the output is disabled. This totally depends upon the type of transceiver, and the selection pins are subjected to 10 positive and 10 negative SAPs in the ESD test. Moving on, one thing that I would like to mention here is the difference of system level ESD and component level ESD. The component level ESD is also known as human body model, which is always seen in the datasheet of a transceiver part. Human body model is the popular component model for ESD standards. Note that these are the model considering a controlled environment, means the ESD levels present here are not that severe. It means when you model HBM, we have taken some ESD precautions. Whereas in the case of a system level ESD, like IEC 61000-4-2, there are no ESD precautions, and the environment is considered to be uncontrolled, and the ESD can be very, very severe in that case. So this difference can be, the difference between these two type of waveforms can be interpreted from the graph. Waveform in red represents an IEC 61000 4-2 ESD, whereas blue represent a HBM ESD waveform. Note that the IEC 61000-4-2 ESD waveform has very short rise time and high current during the rise time. So this can be seen from the table above. So an IEC strike of 2 kilovolt might not be survived by 2 kilovolt human body model. So when we choose a component, we need to make sure that we are adhering to the correct test standard. Also note that majority of the energy of an IEC strike is contained in the first 30 nanosecond as against HBM model. And IEC specifies 10 positive and 10 negative SAPs against 3 positive and 3 negative SAPs in an HBM model. So for a robust design, we should consider IEC test method. Now let us discuss the next transient, which is the IEC 61000-4-4 with the electric fast transient. EFT testing involves coupling a number of extremely fast transients onto the signal or power supply port of the transceiver. In general, EFTs are generated by external switching circuits that could be inductive or capacitive in nature. These transients are capacitively coupled to the system via communication or power ports. One such example is the relay switching in industrial environments. So in the right side, we can see the EFD waveform. These waveforms are generated by passing them on to a 50 ohm load and capturing them using a DSO. Each individual pulses have a rise time of 5 nanosecond and pulse width of 50 nanosecond. Approximately same that of an ESD, but little slower with 5 nanosecond rise time. These pulses are applied with the repetition rate of 5 kilohertz for 5 millisecond or 100 kilohertz for 750 microsecond. And the burst is applied with an interval of 300 millisecond. Table on the left bottom side shows the test voltages and associated test levels. EFT is performed using a coupling clamp in the test scenario. This is basically a capacitive coupling clamp for signal and control ports. The clamp is shown in top right. In case if you are unable to use a coupling clamp, then we are suggested to use capacitors. And these coupling capacitors values can vary from 100 picofarad to 1000 picofarad. The capacitor value depend upon many parameters like cable diameter, material and cable shield, etc. So in case of but in the case of power port, we can use only 33 nanofarad capacitor. For ADA transceivers, we typically test signal port and control ports meeting all these standards. The right side picture shows a typical test setup for our isolated 485 transceivers. We test the part with respect to ground 1 and ground 2. The isolation barrier present between ground 1 and ground 2 is designed to withstand high voltages using our I-coupler technology. And also there are protection mechanisms inbuilt to the IC against EFT pulses. Now, let us look at the next IEC transient, which is the surge. This is IEC 61000-4-5, and surges are mostly caused by lightning or switching transients. Lightning strike may cause direct strike, or it induce voltage and current due to indirect strike. Switching transients are caused by power system switching or load changes in the power system, or by short circuits or fault conditions in the power system. Switching inductive loads also creates transients. Shown in the top right is a 1.2 microsecond rise time and 50 microsecond pulse duration open circuit waveform found in the IEC surge test specification. Note that the short circuit current associated with this waveform is having a rise time of 8 microsecond and a pulse duration of 20 microsecond. Earlier, there used to be one more surge test wherein the rise time used to be 10 microsecond and the pulse width used to be 700 microsecond. But this test is excluded recently from the IEC test standard. Also note that the surge generator usually has an output impedance of 2 ohm. That implies 2000 amps for a 4 kV surge. So we need to be very careful while choosing the coupling and decoupling network for the surge test. This slide basically give you an overview about surge test setup. While conducting the test, if the test uses an unshielded cable, we are allowed to use two numbers of 80 ohm resistor in parallel. You can see that in the test diagram shown in the left hand side. It also implies for a 4 kV surge, the effective current pulse is only 47.6 amps. That is just because you have 80 ohm resistors in parallel. And for an asymmetrical shielded cable, it's about 40 ohm and the peak current is about 95 amps. Whereas in the case of a shielded cable, there is no coupling network permitted and the peak current can go up to 2000 amps. So it is very important to know the choice of cable to select the appropriate protection circuitry, because your current might vary based on the cable selection. In ADI, we use 80 ohm in parallel for unshielded cable and no coupling network in the case of a shielded cable while conducting the test. In the upcoming slides, we will discuss conducted immunity IEC 61000-4-6, direct power injection, which is IEC 62132-4, and fault protection mechanism, which are highly important for a system noise immunity and robustness for a systems. Let us start with system level noise immunity test IEC 61000-4-6, the conducted RF. This test is applicable for products operating in environments where radio frequency fields are present. As you know, the source of disturbances are electromagnetic fields that might act on the whole length of your cable and that is connected to the equipment. In the test setup, the RF voltage is swept from 150 kilohertz to 80 megahertz with amplitude modulated sine wave of 80% at 1 kilohertz. And this sine wave is coupled onto the circuitry using a coupling clamp shown in the top right. In ADI, we conduct the test and our objective is to pass class A criteria with 10 volt amplitude. The test is conducted with respect to ground 1 and ground 2 with both shielded and twisted pairs. Please refer IEC 61000-4-6 to know more about the test method. Now let us look at the VDD noise immunity test, which is the IEC 62132-4. It is also called a direct power injection. In case of VDD noise immunity test, we are going to talk about IEC level. We are going to talk about IC level than system level test. Here we are going to use direct power injection for VDD noise immunity test. During the test, RF disturbances in the form of sinusoidal waveform with the frequency varying from 150 kilohertz to 1 gigahertz is injected into components VDD pin. This is done via a coupling capacitor. You can see that in the test circuit. At the same time, the power is increased at each frequency. The pass or fail criteria is decided looking at the bit width change of the transceiver. For a pass criteria, the code width should not vary beyond plus or minus 10% at any of the frequency. Look at the diagram. We can see a 6.8 nanofarad capacitor is used to inject the noise to the VDD pin of the IC. The inductors are used to make sure that noise is not going to the local power supply filtering, reducing the severity of the test. The image on the top right shows the test setup, which uses a sine wave generator, power amplifier and a DUT with coupling mechanisms to inject noise into VDD pin of the IC. Okay. This slide basically shows the result of an immunity test conducted on VDD1 and VDD2 of the transceiver. In this test, we have basically considered three technologies. I mean the isolation technologies. One from our competitor too, which is the capacitive isolation technology. In graph, green line shows ADI's OOK technology. Here OOK stands for on-off keying technology. And blue represents competitors' capacitive technology, and the orange represents ADI's older isolation technology, which is the 1 pulse to 2 pulse encoding scheme. And you can see that the on-off keying technology represented by green line shows superior performance against the others, especially in the band of 100 megahertz to 300 megahertz. During this band, you can observe the deterioration of the competitor's capacitive technology, and eventually these parts are damaged permanently, which are denoted by the cross mark in the graph. Also, you can observe that the test results holds good for the same way for VDD2 test also. Now, in this slide, we will talk about the importance of fault protection requirements for a reliable operation of the equipment during and after the installation. As you know, most of the time, the power and the signal cable run together. Any misfiring, as shown in the bottom diagram, can damage the transceiver permanently. Providing a continuous overvoltage protection of plus or minus 42 volt make the system robust in majority of the applications. Secondly, the 48 cables run for long distance, maybe up to few kilometers, which means there could be potential increase in common mode voltage across the cable, enabling a 48 transceiver to handle an extended common mode voltage of plus or minus 25 volt will definitely address these system level challenges. Again, operating temperature is a important parameter, especially in the industrial environments like oil and gases, military and aerospace. Having a temperature range of minus 42 plus 125 is very good. So ADS new generation 48 transceivers are designed to meet all these requirements. System level design challenges. Upcoming slides, we will discuss briefly about the radiated emission requirement of the system, and these requirements are specified under EN 55022. Let us briefly discuss EN 55022 or the FCC radiated emission requirements. With our isolated 485 parts, we are meeting EN 55022 Class B emission standards. The above image shows a typical test setup for the radiated emission test. The device under test is placed 10 meters away from the antenna. The antenna can be adjusted from 1 meter to 4 meter above the ground. Along with this setup, there is a spectrum analyzer to capture and measure the peak and quasi-peak emissions. You can see that FCC and CISPR Class B emission limits on right-hand side graph. Meeting Class B emission limit is the most desirable criteria when we talk about emissions. With our transceivers, we are trying to meet EN 55022 Class B limits. That goes up to 230 megahertz with 30 dB limits, and up to 1 gigahertz with 37 dB limit. So our transceiver performance you can see in the coming slide. This slide basically shows the emission performance of our transceiver with on-off keying technology. From the test result, you can see that we are typically 6 dB margin on EN 55022 Class B emission standards. With this, I conclude the IEC test standards. Of course, not all, but important generic standards for system level reliability and robustness. Now, we will see an overview of ADI's system level solutions, Fieldbus application concerns. Here I am introducing our part ADM2795E, which is industry's first IEC level 4 surge protected RS485 transceiver. This part offers significant EMC performance against parts that are available today in the market. ADM2795E integrates analog devices I-coupler technology for the robust isolation requirements, and it's offering about 5 kilovolt RMS isolation. Such a high-level isolation ensures reliable operation in harsh environments. ADM 2795E offer complete system level solution, and the part is compliant to IEC 61000-4-2, which is the level 4 ESD test, and which calls for plus or minus 8 kV contact discharge and plus or minus 15 kV air discharge. It also complies to IEC 61000-4-4, the level 4 EFT test, and the EFT levels are up to 2 kV. It complies to the level 4 surge test, which is IEC 61000-4-5, and here the surge levels are up to 4 kV. And the part is also compliant to IEC 61000-4-6, level 3 conducted immunity test. ADM 2795E further improves system level reliability by plus or minus 42 volt fault protection feature on its bus pins. The part also offers extended common mode voltage range of plus or minus 25 volt, which ensures reliable communication over long distance. So to make the long story short, ADM 2795E can help pass the stringent IEC EMC test easily, and it can reduce the EMC certification process. The part also saves board real estate with integration, and it's a single chip system level solution. Moving on, we do offer a non-isolated version of the ADM 2795E, which is ADM 3095E. This part is offered in enhanced package for military and aerospace applications. In addition to the robust EMC performance of ADM 2795E, it also brings many other features onto the table. Let us have a look at these features. The ADM 2795E has a logic interface voltage ranging from 1.7 volt to 5.5 volt, which helps to interface the part seamlessly with any MCU and FPGA, right? This part is fully compliant to RS485 and RS422 protocol and standards, with operating voltage range of 3.3 volt to 5.5 volt, which makes this part especially suitable for long distance communications. And the part is also compliant with Profibus with a 4.5 volt supply at the isolated side. The part can support up to 256 nodes with extended common mode voltage range of plus or minus 25 volt, and is tested for standards like Profibus, Modbus, and BACnet. This slide provides a nice summary on our solution. ADM 2795E is an innovative solution that helps reduce PCB area, and it helps to pass stringent IEC test standards, and it also makes EMC certification process very easy. And it also provides fault protection on bus pins to protect the transceiver against miswiring and over voltage conditions. The picture on the top right side shows a discrete implementation scheme that pass IEC level 4 ESD, EFT, and surge test. You can realize the number of components, board space that you need to have here. So ADM 2795E is the compact solution that reduces design cycle time, and it also reduces the EMC iteration in your design. Now, let us look at application examples of ADM 2795E. It gives a significant application level impact. For example, industrial automation and transmission and distribution business. In particular, industrial automation application do have PLC communication ports, and those ports are subjected to large common mode voltages from the potential differences, and they are also subjected to miswiring faults. So the features of ADM 2795E can be the best fit here. And in case of built-in technology, as you know, there are multi-story cables and are subjected to interference from voltage lines or switching voltages from motors. So the IEC level protection incorporated to ADM 2795E uh, helps to protect against all these transients. Similarly, in aerospace and military applications, engine controls and actuator controls are using 485 communication. And ADM 2795E's isolation barrier is tested against DO 160 section 22 for lightning protection. Now, let us examine how good is ADM 2795E against the solutions available today in the market. At the very first glance, we can find that ADM 2795E is providing feature-rich solution against the competition. As you can see, none of the competitor part provides the complete feature set that ADM 2795E is providing. Look at the features highlighted in green. In case of competition, these features are spread across different product families. Also, you can see that ADM 2795E provides complete set of IEC protection level against competition, regardless of the logic and power supply requirements. ADM 2795E is compact, cost optimized, and integrated solution, and it offers IEC level protection in reduced PCB area. Now, I just want to give you an overview about the 485 roadmap. Today, ADI is providing highly integrated and robust RS485 solution to customers. For example, ADM 2587E is the market leader in integrating both power and signal isolation. And it is the smallest isolated RS485 transceiver available in the market today. The same product family offer both half and full duplex communication with high and low speed options. There is also another part which is LTM 2881, which integrates both power and isolation. In addition to that, it has inbuilt termination resistor for an easy implementation. We also offer set of non-isolated RS485 portfolio. For example, ADM 485E and ADM 487E family of products. These parts, the parts like ADM 1487 in the product family offer complete Profibus compliance with full and half duplex options. ADM 2795E and ADM 3095E provides complete system level EMC solution for communication ports. And there is also a family of product which is LTC 2862, 2863, 2864 and 2865, which provides plus or minus 60 volt fault protection for the RS485 or 422 bus pins. In this slide, provides overview about the supports and collaterals available for ADM 2795E. ADM 2795E evaluation boards are available today for customers. These evaluation boards are tested and certified to conform EMC test standards, that is the IEC 61000 standards. The complete certification details are available from analog devices upon request, and the IBIS models are also available for ADM 2795E for the simulation. Please check our website for application notes and white papers on RS485 or RS422 design implementation scheme. One such example is the AN960, which talks about rugged 485 implementation schemes. And the CSA, UL and VDE certification for our isolation is also available in our website. And with this, I want to conclude my discussion on the solutions, and I am open for any questions for next 10-15 minutes. Um, uh, there is a question um wherein the question is like whether ADM 2795E helps in analog communication. Um, can you rephrase this question? I am not very clear. So I believe the question is asking whether the ADM 2795E can be used to transmit analog signals. If that is the question, no. The ADM 2795E uh, basically 485 transceiver. So the output is always your differential voltages. So it's not meant for the analog isolation. Another question is about the board spacing that we can achieve using ADM 2795E. Um, so as explained in the previous solution, for a discrete implementation, you need to have all the protection components, the isolation and the transceiver to meet the level 4 EMC test standard. So comparing against a discrete solution, we can have 30 to 40 percentage board space saving, especially if you have to incorporate GDTs and other thing for the surge protection. That too up to 4 kV of surge. So in any case, we'll be able to meet 30 to 40 percentage space saving with ADM 2795E. So another question is like other methods by which we can protect a device from ESD. Uh, so as I so here, if we are not going to use ADM2795E, and if you want to protect your circuit against ESD, uh, we have to use a combination of protection schemes, which will have ESD diodes, which may be unidirectional or bidirectional TVS diodes, and you may have a current limiting device. It could be a, a resistor, or it could be a tips kind of part. And if and you might have a GDT if you are expecting surge. But if you are worried only about the ESD, then TVS diodes and tips can help you. In some cases, you can use a series resistor, but it depends upon the speed of communication and the length of the cable, because the as the length of the cable goes, you have a increased capacitance coming into picture. And at the transceiver side, you have a pin capacitance, and you have a series resistor to limit the current. So the combination of this capacitor and resistor basically limits your data rate. But if you're having a very low data rate applications, yes, you can protect your device against ESD using TVS diodes and a series resistor. If you need high speed and you need the protection, then you have to go for a combination of TVS diode and the tips. Another option is you can use the transceivers from analog devices, which gives you very high level of ESD protection. The ESD functional level ESD protections goes up to plus or minus 50 kV. So these are the ways and means uh, we can protect our device from ESD events. Another question is how to protect it from EM radiation. I'm not clear about this question, but if it's a subsequent question to the earlier one, then these are two different types of tests, and the mechanism to protect your circuit against EM radiation is different. Um, Explaining more about EM radiation, probably you can contact me on my email address, or I will send it to you offline, the methods that can be used. There are many ways you can do it. You have to take care of the proper cabling. You have to take care in your PCB design. Then you have to take care. You have to see whether your design is capable. Your design is going to have a earth connection, or your design is able to accommodate a chassis which is metal. So all these things come into picture. So other question is about the TISP. Should we use bidirectional or unidirectional TISP? Basically, this replaces it basically block the current, and it's a bidirectional device. As the current goes beyond a limit, it just open up. So we really don't have to worry about the direction in that case. So there is another question uh, uh, wherein it's asked about variable frequency drive, and at present they are not using any electromagnetic protection for the VFD. And is there a way we can protect it? So in the third or fourth slide, I explained about the methods wherein we can approach electromagnetic compatibility, which is the band-aid approach and the system level approach. Since your product is already designed, you have only band-aid approach. That means all your solutions are going to be costly to overcome to accomplish this electromagnetic compatibility. Until and unless you do, if you're not redesigning your board, then there are costly solutions available to protect your device. I think I can address one more question, and we can end this section if you don't have any other questions. There is another question which is asked. So the question is, ADM 2795V looks like an interesting solution when it comes to complying with EMC level 4 standards. Do you also have a variant where power isolation is also integrated with the IC? What would be the impact on RE with the power isolation integrated? Yes. So we have the solutions which integrates both power and data isolation. Those parts are ADM 2587E and ADM 2687E and the LTM 2881. And with regard to the radiated emission question, we do have the design techniques in place which will help you to pass the class B emission standard. So we really don't have to worry about the RE with our power and data integrated RS485 transceivers. Yeah, I think thanks everyone. Thanks for attending this webinar session. I believe it was useful and informative to all of you, and you will have a. I believe you have an idea about the way when we have to design the communication ports for industrial applications when it comes to RS 485 communication ports. Thank you. Thank you